Thank you very much. Can you hear me louder?
Yes. Yes.
Thank you. And now you should see my screen. Is it okay?
Yes. Yes.
Thank you very much. So first of all, I would like to thank the organizers for giving me the opportunity to present our work. And today I will show you a way in which the NO2 sensitivity can be improved by a simple tuning of the substrate architecture at room temperature. Why at room temperature and why nitrogen dioxide detection? It's important to detect the nitrogen dioxide because it's a highly oxidizing gas, which is really harmful for humans and for flora and fauna. And the need for room temperature detection, it's needed in order to decrease the power consumption. So the integration of this kind of devices with which are able to detect NO2 at low power, having low power consumption. However, there are plenty of publications in the field of gas sensing dealing with NO2 at room temperature, like these Chinese guys here, which they claim that they have made it to detect NO2 at room temperature, but without taking into consideration the in-field conditions. What I mean by in-field conditions is the presence of relative humidity, which is the main interfering gas, and the other target gases, which might be present also in the field, like CO2, H2S, methane, or ammonia, or so on and so forth. So we have in our lab experimental facilities which are able to mimic the in-field conditions. So basically, we have plenty of gases which are toxic and explosive gases, which can be mixed with the relative humidity under controlled conditions from ppm, from ppb to ppm levels. And we can measure different sensitive materials deposited onto this kind of planar substrates, which they are not basically sensors. They are substrates which we are dealing with, but they are compatible with any kind of industrial substrates which can be transferred into the industry. What have we done? We have looked, first of all, to tin dioxide, which is the well-known sensitive material for NO2 and other target gases. But we doped this tin dioxide with manganese in 10, 20, and 30%. What can be seen here is that the sensor signal towards relative humidity decreases as the manganese concentration increases. So from black curve to red curve. This means that we choose tin dioxide base with 30% of manganese due to the fact that has the lower interference with the relative humidity. And we go further with this material and we test it towards NO2 concentration from 0.8 ppm to 7 ppm. And as one can see, someone has the microphone open. As one can see, the sensitivity, it's kind of linear for the tin dioxide doped with 30% manganese, besides all the other sensors. And what I would like to bear in mind for you is the fact that we have the average crystallite size of 8 nanometers. This is quite important because I will do some modeling later on. And I will focus on this 8 nanometer tin dioxide crystallite size average. Okay, nothing special from the XRD and SEM and EDS analysis, besides the fact that we are dealing with polycrystalline thick film sensor deposited on as I told you, planar substrates provided with interdigital platinum electrodes. The morphological investigations as well, they showed us that we are having a quasi-spherical nanoparticles with the average size of 8 nanometers. And now there are several points to increase the sensitivity. Besides the nanostructure, increasing the surface area by noble metal decoration or doping or so on and so forth, herein we focused on substrate architecture. What I mean by substrate architecture is that we can increase the sensitivity by varying the interdigital distance of the platinum interdigital electrodes. And I'll show you how. We are dealing with a thick film material of about 2 or 3 micrometers, deposited, as I told you, on these planar substrates. And what you can see here is a representation of the grain-to-grain crystallite boundaries in terms of an RC and R series equivalent circuits. Why it's so important? It's important because you have to know that we are dealing with tin dioxide, especially, which has low resistivity in the bulk because it's full of electrons, and the surface which is depleted of electrons, and the electrons from the bulk have to jump over this potential barrier at the surface in order to take place to the conduction. And this is represented by the RC circuit in parallel here at the grain-to-grain crystalline boundaries. Now we have done some simple mathematics, taking into consideration the Schottky approximation and the Poisson equation, that we allowed us to write the RC as an exponential of a potential barrier divided by kBt. The same thing is for the grain-to-grain boundary here in the right-hand side, the exponential of a potential barrier, the grain-to-grain boundary, this time divided by kBt. And what we are having basically a sum of the RC circuit, which are in parallel, representing the metal semiconductor contact, and plus the number of crystallites which are existing between the interdigital electrodes, minus number of fingers, because we are, as I will show you later on, we are dealing with 200 and 100 micrometers distance between the interdigital electrodes, exponential by the QVS over kBt. Well, now it's a more realistic approach. On the right-hand side, we have the substrate, which are having 100 and 200 micrometers. And here I have represented the RC circuits, which are dealing with the grain-to-grain boundaries, which are responsible for the increase in the sensor signal, and the RC circuits, which are responsible for the platinum to semiconductor metal semiconductor contact, which are basically a dead representing equivalent circuits. They are not contributing, they do not bring any contribution to the sensing effects. So in fact, as more RC circuits between grain-to-grain boundaries we have, the more sensor signal it is. So this is what we saw experimentally. We have plotted the sensor signal versus NO2 concentrations for tin dioxide doped with 30% of manganese under 50% of relative humidity at room temperature. As one can see, up to 3 ppm of NO2, nothing is happening between the sensor signal between these two kind of substrates. But after 3 ppm, there is a strong increase in the sensor signal for the 200 micrometers interdigital distance for the substrate. This means that we have more and more grain-to-grain boundaries which are active for the sensing performances there. We have done a simulation with all the mathematics which I showed you before. And as one can see, as the sensor signal increases with the decrease in the grain size, which is obvious because we will have more grain-to-grain boundaries. And as smaller the grains are, the higher the sensor signal is. And moreover, we saw that for 200 micrometers, the values are close to the experimental one with our mathematics. So which are representing a good approach, because this means that we didn't mess up all the things in our calculations. In conclusions and outlook, we could see that the geometry, charge transfer, and equivalent resistance can be split up in order to bring their own contribution to the enhanced sensitivity. And moreover, this can be evaluated for long-term stability or other kind of interfering gases as a way to optimize the material for environmental monitoring, or why not industrial site effects. I would like to acknowledge this this financial support for two projects for bringing me the money effectively to my work, and thank you for your attention. If you have questions.
Thank you very much for your presentation. If you have any question or online question. No, thank you again for your presentation. Okay, our next speaker.
Thank you, thank you.
Thank you. Our next speaker is from India. I don't know if it is online. Mr. Rakesh Kaur, I hope I pronounce correctly. Mr. Rakesh Kaur from India.
Seems like he's not online.
Okay, in this case, Mr. Simeon, do you want to present the next speaker?
Sure. If our fellow from India is not online, I would like to introduce Ioana Ion from National Institute for Research and Development in Electrical Engineering, with the work entitled Improvement of Hydrogen's Properties by Addition of Graphene Oxide.
Thank you. My name is Ioana. The title of my presentation is Improvement of the Hydrogel Properties by Addition of Graphene Oxide. Okay, just a moment. Share. A little, excuse me. I have a small problem with sharing the presentation.
Would you like us to share it?
Okay, I'm sharing, but I don't see on the screen. The camera is open, the microphone is open.
Yeah, we also can see your first slide.
First slide, okay.
Yes.
My name is Ioana. The title of my presentation is Improvement of Hydrogel Properties by Addition of Graphene Oxide. Okay. Abstract, and we begin with the introduction. Polymeric hydrogen is a large class of materials which are a hotspot in the last decades of research because have a complex structure. These are related to possibility to obtain this from many type of polymers and have the possibility to obtain by a few a few methods like chemical cross-linking and physical cross-linking and mixing method. And for this reason, the polymeric hydrogen have a lot of a large type of properties with a large type of application. The polymeric hydrogen in general consists of three-dimensional networks of polymer which are insoluble in water, and because of the functional groups which are contained on his caten, have the possibility to absorb a large amount of water. But the major limitation of the polymeric hydrogel is their low mechanical stability in hydrated stage and harsh environmental condition. Harsh environmental condition means very acid or very basic pH. To overcome this challenge, a lot of researchers and research papers are focused in improving these properties. Our study, the same, have the principal aim to improve the mechanical properties of hydrogel, adding graphene oxide, and to find a suitable preparation method, made a comparison before the properties of the hydrogel obtained by physical cross-linking means freezing throw cycle, and the mixed method, which are consist of free throw cycle and the gamma irradiation cross-linking. The graphene oxide was prepared by modified method, and the principal aim of his addition in the composition was to increase the strength and to prove antibacterial properties. To understand more the gel, I want to present a little to description in the as definition, new pack definition, classification, and in polymeric science dictionary. This was for UPAC definition, non-fluid colloidal network made of 3D network, which are expanded by a fluid, and the definition of gel by polymer science in the polymer science dictionary was a cross-linked polymer solvent by on solvents. The gel are classified in four principal classes: hydrogel, organogel, xerogel, aerogel. Difference between them are the fluid. And for the last two, the method of preparation. The most important in this field is hydrogel and xerogel. Difference between hydrogel and xerogel is that the insoluble polymers, this means the not cross-linking polymers are not present in the xerogel, and the fluid is water for the hydrogel and air for the xerogel. Materials and method. We prepare four hydrogels using one composition and addition of graphene oxide to increase his mechanical properties in hydrated state. And the second was to prepare this by two types of preparation method, physical and mixed method, to find a suitable one from them for mechanical mechanical enhancement. The principle of the physical method is that the cross-linking is made by hydrogen bond. In comparison, the preparation using gamma irradiation method is a covalent bond. mixed method have the properties from the Bose method, have hydrogel bond and covalent bond, and supplementary from the gamma irradiation method. This complex method, mixed method, bring the same additional sterilization of the final product. Composition was 5% of polymer. The polymer was a blend made of PVA and PVP and like plasticizant, glycerin or glycol. Starting compounds and motivation. Why I'm using this? I'm using 20% of PVA because in the literature ARC know that addition of PVA increase the mechanical strength, increase the porosity, present a weak antibacterial effect, and increase the hydrophilicity, being a very hydrophilic polymers. The addition of graphene oxide was made because in literature is known that the addition of graphene oxide, which have a doide structure, to D structure, increase the mechanical strength, present a biocidal effect, and increase the photocatalytic effect, and not in the end, together with another semiconductor, can enhance the photocatalytic or catalytic properties if are added in the hydrogel, and in this way increase the decoloration of the methylene blue in the hydrogels used in water remediation. In the figure 1 are present the solution of gel, and in the fig 2 are present the film. The solution was cast in the Petri dish. These are the first Petri dish before to be dry and use film, and or to be freeze to obtain hydrogel. First method to obtain hydrogel was a physical one. The mechanism of hydrogel formation by freezing thawing method. This means a physical cross-linking using hydrogel bond is present in the scheme, and in the left and the right are the Petri dish with the polymer in the polymeric solution, and in the right are in the freezing stage. Antifungal effect of the graphene oxide added on the hydrogel composition. The hydrogel composition was infested with mold, and present a mold infestation after 7 days, 40 days, and 21 days. And the infestation look different in function of the hydrogel method, obtaining method. The mold infestation are presented only on the hydrogel without graphene oxide. In the base of the picture with brown color are the hydrogel with graphene oxide. The mold has a different appearance depending on the preparation method of the hydrogel. The constriction is more pronounced for the irradiated hydrogel and higher for the hydrogel with graphene oxide, and vanish in the time because of evaporation. How we can see in the picture, after the irradiation, the constriction are a little more higher, because after the irradiation, additional cross-linking of the polymeric chain are obtained, lead in this way to a small constriction. Antifugal effect of the added hydrogel in composition of veșul preparated method are present in this picture. In the left, it's non-irradiate hydrogen. In the right, the irradiate hydrogen. And in this way, we can see more clear the effect of irradiation. In the picture from the back are present a macro from the hydrogel with infested zone. They look very different from irradiated and not irradiated sample. In which way? In the way that the infestation is deeper and on large area for the non-irradiate hydrogel, and for the hydrogel irradiate, we can see a small area infested, more concentrate, and network of the mold, it's more on the surface than inside. The same, the constriction phenomenon, it's more pronounced for the hydrogel which was obtained with irradiation. The same because the irradiation bring additional cross-linking of the polymers. Swelling ration, equilibrium swelling ration. These are the most important characteristic of the hydrogel, of course, which are give the information about the water content and swelling properties, and they are increased with increasing the with the addition of graphene oxide. The difference are not too big, but enough, and a small difference are presented for the hydrogel irradiated hydrogel, because the additional of cross-linking lead to the decrease in swelling degree. In the picture are present the hydrogel after was immersed in methylene blue solution, and dry hydrogel in the bottom of the picture for the both method. Thermal analysis by DSC technique was made. Not big difference between the film hydrogel irradiate or not irradiate. In the DSC curve we can see the properties, very high hydrophilic properties of PVA, the first cycle, blue cycle, and in the other blue cycle are present a small difference which are not significant modification bring by the addition of graphene oxide and the addition of the the irradiation of the sample. There is not big difference, not significant difference in the thermal properties of the film of the irradiate or not irradiated hydrogel. This because the cross-linking degree are small. Why we obtain to have a small cross-linking degree? Because the cross-linking degree are directly related with the absorption properties. In which way? If the cross-linking degree is high, the absorption properties are small. For this reason, we adopt a small irradiation dose, 25 kilogray, and a few freeze throwing cycle, which was during just 3 days. In the end, the conclusion of this preliminary research was the preparation method is important. If you tune attentively the method and the composition, we can tune the final properties of the hydrogel. The sterilization by gamma irradiation is very important. the additional cross-linking reaction, which are determined by gamma irradiation, the same can influence the cross-linking degree and the swelling degree and water uptake and absorption degree. And composition, the same is very important. The addition of PVA transform the hydrogel, the addition of PVP, excuse me, in the PVA transform the hydrogel in the biodegradable one, which can be used with successful in case of discharge and neutralization by biodegradation. Graphene oxide is very clear, have antifungal effect at a small quantity, 0.05%, and this lead to the to stop the infestation with mold, and the infestation the infestation was stopped, but was impeded, but not stopped by sterilization using gamma irradiation, because the accumulated dose was small, 25 kilogray. This is the result. For more information and we have a future work to to find the suitable composition of this hydrogen, and for this reason you have more information about thermal treatment. For this reason we will be perform another thermal analysis like TGDSC, and in the end the results are very are good, and find a new route to develop biodegradable hydrogel with antifungal effect if you add graphene oxide in small quantity. And maybe in the future will be decrease the quantity of the graphene oxide to obtain a transparent hydrogel, because was not very transparent at this concentration. And another important information obtained from this work was the physical cross-linking lead to opaque hydrogel, which are not very good in photocatalytical application. This was all. Thank you for your attention.
Thank you for the presentation. If someone has questions from the audience, from the online.
No.
No, if not, let's thank again the speaker.
Thank you very much.
Thank you.
Thank you.
And Ms. Mochoyu, I'm giving you the microphone right now to continue.
Yes,
This
was the last presentation. I want to thank to my colleague which helped me to present section 3. And now I want to Mr. Simeon, and now I want to give the word to our scientific manager to tell us what happened with the poster presentation.
Okay, thank you. So once again, I'm reminding you the sponsors of EMERGEMAT 2025. So it is about the Ministry of Education and Research, about the European Technological Platform on sustainable mineral resources, and two Romanian companies, Altium and Nanoteam. The next part of our event consists of the poster presentations. Right now, in the hall, all the posters sent to our event are run in a slideshow. People present here in the hall can see them. For the rest of people attending our conference in online, it is possible to access each and every poster on the website of the conference. But as we asked before, there are 5 people who want to present their posters online, and they are Bogdan Postolnei, Cristina Firincă, Diana Hanganu, Călin Licu și Larisa Stroie. If there is anyone ready for his or her presentation, please raise your hand and let's proceed. Okay, it seems that Dr. Bogdan Postolnei is ready. So, please.
Hello. May I share the screen with my poster?
Miss Ioana, can you stop sharing? Ioana, you didn't stop your share screen. Okay, thank you. Bogdan, you can share now.
Okay, one moment. Okay, unfortunately, this is the issue with Microsoft Teams. Okay, one moment, if maybe I will succeed.
We move to, for sure, to each poster, and for posterity, we will shoot the presentations on camera. Okay, thank you.
Okay, now I think I can share finally. Okay, sorry for the delay. Can you see the screen?
Yes, please.
Okay.
Go down.
I cut my poster for the parts for better visibility. So since I have just 1-2 minutes, this is the short speech.
Yeah, sorry for interruption. Could be 5 because you are not too many online to.
Oh, okay, nice.
Okay, not 25.
Okay. Anyway, so the main intention is just to invite you to go to the website of EMERGEMAT conference to access the folder with the posters, and you can find the poster there for more details. First, I would like to say thank you for the organizers for such a great conference, which goes annually, and it's very nice. So I would like to present the poster about some initial research which started to do. This is kind of extension to the topic which the colleague Madalina already presented today in the previous sessions. This is on high entropy alloys, namely for antimicrobial high entropy alloys for mitigation of microbiological influence corrosion. And as already was discussed today, so high entropy alloys are the alloys with 5 or more principal elements with the composition from 5 to 35 atomic percents. And they have different set of advantages in comparison to traditional alloys. And so here you can see the one of the figures we created for our review paper on high entropy alloys for SWOT analysis of their properties and applications. So you can also check that on the poster online. So there are like systematic analysis of strengths, weaknesses, opportunities, and threats. Okay, here's the guy, maybe someone of you who watched Lord of the Rings and the new serials about that. So this is the hero who was looking for the ring of power and looking for different type of alloys from which he can do this. So perhaps if he knows about high entropy alloys at that time, maybe he would select such kind of alloys. So what is the idea of this research? This is about one of the advantage and at the same time disadvantage of high entropy alloys is the vast compositional space. And there are like millions of combinations of compositions which can be used for the design of alloys. And by the traditional way, it's kind of time-consuming procedure to do all of type of experiments. And nowadays, one of the approach which is the most effective for materials with complex composition spaces, which requires optimization across multiple variations, is the concept of materials acceleration platform, which includes different steps, such as simulation, high throughput synthesis, rapid automated characterization, then data collection and analysis, and then it gives the feedback for prediction models to go to the second cycle of experiments, and in this way to do the best solutions as possible. And here just some analysis of available high throughput synthesis techniques which could be suitable for high entropy alloys fabrication in different methods. And this is just one part of this cycle. So below there is the analysis of opportunities and challenges on application of this concept. And you can see this on the poster in more details. And also, if you access the poster, then you can find the QR code on which you can download for free our recent review in Applied Physics Review on the topic of antimicrobial high entropy alloys for mitigation of microbiological influence corrosion. Thank you so much.
Thank you very much, Bogdan. Are there any questions here in the hall? Online questions, please. Just to scroll for raised hands. It seems not. So let's thank once again Bogdan Postolnei. Thank you. The next poster, Miss Cristina Firinca.
Yes. Can you hear me?
Yes, we can hear you. If
All right. I will start my...
Plan to stop sharing, right? Yeah, okay. The previous poster is off. Okay.
All right. Can you see the screen?
Yes, we can.
Okay, great. Greetings, ladies and gentlemen. My name is Cristina Firinca. I am a PhD student and also a researcher at ECHECHIM. It is a great pleasure to be part of today's conference, and I wish to thank the organizers for that. Now I will present our work. Heavy metal pollution is one of the most important challenges we face currently. and in environmental terms, and most of the conventional treatments available can be costly, disruptive, and generate secondary pollution. Chromium, especially in its hexavalent form, is highly toxic, persistent, and bioaccumulative, making its removal difficult. Also, real-time monitoring is necessary for the long-term assessment of remediation outcomes. That is why we need integrated approaches that are more sustainable, efficient, and sensitive. In that sense, our research aims to develop a complex system that combines a fungal consortium, highly efficient in chromium bioremediation, and real-time monitoring through an electrochemical device based on nanomaterial modified screen-printed sensors. We have isolated fungal strains from soil highly contaminated with chromium in Bucharest, and we have selected the most suitable ones based on compatibility and tolerance to high concentrations of potassium bichromate. The novel consortium formed was applied onto soils with different levels of chromium contamination and compared with an individual strain in similar conditions. The elemental composition of the soil samples was assessed by X-ray fluorescence, and variations in pH levels were monitored after 8 weeks. We have observed a direct correlation between soil acidification and chromium bioleaching, resulted from the production of organic acids and other metabolites by the fungal strains. The reduction of hexavalent chromium concentration was monitored in soil solutions extracted with small volume lysimeters by amperometric detection using screen-printed carbon paste electrodes modified with Prussian blue by electrodeposition. The developed sensor presented high sensitivity and accuracy, allowing us to observe an almost complete reduction in the concentration of hexavalent chromium after 8 weeks by treating our soil samples with the fungal consortium. Thus, the scope of our study was achieved, and we will continue by evaluating the phytoextraction efficiency of hyperaccumulator plants for eco-restoration and chromium recovery from contaminated soils. Thank you for your attention.
Thank you. If there are questions, yeah, sorry, first. From online? Nobody. Okay, Miss Cristina, thank you once again.
Thank you very much as well.
The next presentation, Miss Diana Hanganu.
Hi.
Hello. We can hear you. Please share your poster.
Okay, please tell me if you can see the presentation.
Yes, we can see it, sorry.
Oh, thank you. I will make it step by step just to be easier to follow. And after that, I will make it full screen. First of all, thank you everyone for letting me and allowing me to be here to present the work conducted alongside my teamwork. In the first place, I would like to make a little bit of a background because I know that everyone is accommodated in knowing that the pharmaceutical compounds creates a general problem with a negative impact on the environment because their presence have toxic effects on aquatic life. So we are trying to remove those pollutants with different methods, starting with adsorption, the most commonly known removal method. In this study, we synthesized a new material, nanocomposite, based on carbon nanofibers with copper oxide and zinc oxide, used as an adsorbent for ceftriaxone, an antibiotic. We chose ceftriaxone because it's mostly eliminated unmetabolized from human body, over 90%. So we are trying to remove it to eliminate those toxic effects on the environment. The method of synthesized is a simple method, a co-precipitation method. We made them as materials copper oxide and zinc oxide with and without carbon nanofibers, calcinated for hours at 400 degrees. The samples was characterized before and after calcination. You can see the carbon nanofibers and the oxides that can form an agglomeration over the carbon nanofibers. We did the X-ray diffraction before and after just to see exactly that the hydroxide transformed to oxides after the calcination, the crystallography and the presence of both copper and zinc in the analysis of the material. The testing was made in the laboratory with ceftriaxone. You can see each material tested on ceftriaxone 10 milligrams per liter. The best performance was made with carbon nanofibers decorated with copper oxide and zinc oxide, because we tried with or with and without carbon nanofibers, showing that both the oxides and the carbon nanofibers had an important value in this material. We tried to understand, of course, the mechanism behind it as well. So we dig a little bit deeper. As you can see from the chemical structure of the ceftriaxone, it can form some electrostatic interaction based on the nitrogen atom and the carboxylic group, hydrogen bonding with the oxygen group from ketone and the carboxylic group, the PP interaction, and what is more important is because we have metal oxides in the nanocomposites, it can form some complexations with the carboxylic group from the ceftriaxone, showing that the performance and the efficacy of the material that we synthesized can be used in the future. Of course, the results show this high absorption, and the most important is that they were all made at neutral pH, natural pH of the solution, no needing for the pH regulations, showing several advantages, including its high surface area and its high absorption rate of the pollutant. If you have any question and if you want me to elaborate anything, please ask.
Okay, thank you. So, one question from online. Can we see right? Mr. Paul Constantin. Paul Constantin. Can you hear us? Please unmute the microphone.
No, maybe it wasn't stable.
Scrie ceva în chat. Paul Constantin. Mr. Paun, can you hear us? Raise your hand. Make a sign if you can. Unmute your microphone.
Yes, we can hear you.
Yeah, right now we can hear you too. Is there any questions from you? A question from you?
No,
Or...
no. We don't have any questions. I would like to present the poster that has the main out.
Okay. I see. Let us finishing with the other two presentations, and we are extending our list, and After the first and the second presentation, you will be the third, okay? Thank you.
Thank you very much.
You're welcome. And now, please, Călin Licu, can we proceed with your presentation?
Yeah, sure.
Okay, thank you.
Hope you can see it.
Yes.
All right. So good afternoon, everyone. My name is Mihail Călin Licu. I am a research assistant at Institute of Physical Chemistry, Ilie Murgulescu, and I'll briefly present our work on zinc oxide nanomaterials synthesized by using supercritical water as a reaction medium. The experiments were carried out in our custom-built continuous flow reactor, which is shown in detail in the poster. This method offers several advantages, notably the ability of tuning materials properties such as particle size, crystallinity, and morphology by just adjusting the working parameters represented by temperature, pressure, flow rate, precursor molar ratio, and residence time. The characterization of the synthesized materials were
Sorry, can you unmute your microphone again? Sorry.
Nu se vede. Nu se vede.
Ah, now it's okay. It's okay. Sorry, Mr. Călin, we stopped your microphone by mistake. Sorry, can you open again?
Mr. Călin Licu.
sorry. Yeah. I've seen. I couldn't see in. Firstly, sorry.
Sorry.
I think the microphone stopped when I started the characterization part, which was done by X-ray diffraction that confirmed the formation of a pure hexagonal wurtzite structure of zinc oxide with high crystallinity and preferential growth on the C-axis. Raman spectroscopy showed a strong phonon coupling and low defect scattering that can be translated into better electromechanical coupling and lower losses, features that are favorable for piezoelectric applications. Last but not least, the dynamic light scattering analysis indicated monodispersed particle sizes with an average of 224 nanometers and good hydrodynamic stability. Overall, these results demonstrate that supercritical water can act as a sustainable and efficient reaction medium for material synthesis. Thank you for your attention.
Thank you. Questions, please? From online? No. So, the next poster is from Miss Larisa Stroe. Can you hear us?
Yes. You see my screen?
Yes.
Okay, thank you. Then I will start the presentation. Good afternoon, my name is Larisa Stroe. I'm a PhD student, and today in the following minutes I will present the poster, our work, on the influence of temperature on the material properties of carbon fiber composite manufactured using out-of-autoclave techniques. And this study was carried out in collaboration with the National Institute for Aerospace Research. Out-of-autoclave composite manufacturing is increasingly important in aerospace because it reduces costs and allows for larger structure compared to traditional autoclave methods. However, the curing conditions, particularly temperature, play a critical role in determining the final properties of the composite. Our objective was to investigate how curing at room temperature compares with curing at a slightly elevated temperature of 50 degrees Celsius. We fabricated two carbon fibers composite laminates using the same resin infusion process. Both laminates were made from untreated carbon fibers, arranged in 6 pleats with 90-045 degrees layup using L20 epoxy resin with hardener 161. The first plate was cured at 25 degrees for 25 hours, and the second one at 50 degrees for 12 hours. And in the second case, we used a conductive layer mold. Then after this, we prepared the standardized test specimens by water jet cutting with this method and conduct the tensile test, 3-point bending test, and the heat deflection temperature measurements. And as of findings that show clear differences between these two curing conditions. Stiffness, regarding this, the laminate cured at room temperature shows slightly higher stiffness values, around 70 gigapascals compared to the elevated temperature laminate. Strength and energy absorption, the 50 degrees cured material outperformed the room temperature simple inflexor strength and energy absorption. We had also the increased flexural stress from about 700 megapascals to nearly 1000 megapascals. And we had also some differences in the thermal performance using this method, heat deflection temperature. This confirmed that the curing at 50 degrees provided a higher heat deflection temperature. This indicated as well an improved thermal stability. In summary, cured at ambient temperature leads to higher stiffness, but it compromised tensile strength and thermal resistance. Accelerated curing at 50 degrees improves overall performance, particularly in terms of flexural strength and heat resistance. This highlights the importance of controlling curing temperature in out-of-autoclave process to optimize composite properties, especially for the aerospace applications. Thank you very much for your attention. If you have any questions, feel free and ask me.
Questions? Any online question? No, okay. Once again, thank you to the speaker. And now,
have a nice day.
Mr. Paun, please unmute your microphone and share your poster with us. Good luck.
Good afternoon. Can you hear me?
Yes.
I have to share the poster.
Yes, please.
Unde e posterul?
Păi trebuie să fie la ei, întreabă.
Nu trebuie să-l încarc eu.
Păi da, ei nu l-au.
Okay.
Yeah, we can try, but it will take a little longer because we have to take it.
Can you see it now?
Yeah.
No, you didn't share.
Nu. Trebuie să-i dau share aici.
Share, yeah.
De share?
Intră în desktop.
Nu știu cum să-i dau. Nu știu.
Okay, now we see your screen. Can you put the...
Păi credeam că posterul e la ei, bă, frate.
Okay, now see it.
We can see it.
Cum îl faci mare?
Da. Eu credeam că are posterul ei.
Stai un pic.
Acolo de treabă.
The slideshow.
Slideshow.
Gata. Okay. Can you see it now?
Yeah.
Yes, it's okay.
Yes. Excuse me for the delay. So the poster is, my name is Victor Stoica, and I'm one of the authors. The main author is Costel Păun, and the title of the poster is Studies on the Behavior of Polypropylene Film Capacitors Subjected to Thermal Treatments. The paper studies the behavior of polypropylene film capacitors exposed to heat treatment involving temperature variation. 18 thermal cycles were performed, with temperature ranging from 0 Celsius to 140 Celsius. The effect of the heat treatment on the capacitors' properties was underlined by measuring their capacitance, dissipation factor, and ESR, equivalent series resistance. These measurements revealed changes in the studied parameters and consequently changes in the capacitor structures, offering insights into their degradation under extreme operating conditions. Two capacitors were measured, presented in the left corner, higher left corner, of 4.7 microfarads and 3.3 nanofarads at 400 volts alternating current. Following the measurements, 6 graphs are presented, which show the variation of the capacitance, dissipation factor, and ESR values in the case of the first and the second capacitor. And you can see that after the first cycle of thermal degradation, you can see a significant modification in the parameters, indicating that they made the capacitor performing at lower parameters, as you can see. Capacitors are used in various electronic schemes in many technical applications. During operation, due to environmental factors, electrical disturbances, the internal operating temperature may differ from ideal temperature design for the component, which can accelerate the degradation of the dielectric material. Polypropylene film capacitors are high-quality components used in many applications, especially in power electronics. A polypropylene capacitor consists of two metal foils electrodes separated by a thin layer of polypropylene, the dielectric, both of which are wound together in a cylinder. These foils are then connected to the two terminals of the capacitor, which allow the transfer of the electrical charge between the electrodes, storing energy in the electric field created between them. When a voltage is applied to the capacitor, electrical charges accumulate on the electrodes, with positive charges on one electrode and negative on the other, creating an electric field in the dielectric. Polypropylene, having superior dielectric properties, allows the storage of a large amount of electrical charge, essential for electronic applications where voltage stabilization or signal filtering is required. This paper studies the behavior of polypropylene film capacitors exposed to heat treatment involving temperature variations. The working temperature of the capacitors subjected to the thermal treatment the rated temperatures are between -50 and +105 Celsius. 18 thermal cycles were performed, as you can see in the first small graphic in the center upper part of the poster, with temperature ranging from 0 to 140 Celsius. The capacitor groups were subjected to accelerated thermal aging in a climactic chamber with a program for adjusting the uncontrolled temperature and humidity curve. The humidity was not controlled. The temperature in the device is measured with thermocouple sensors. The upper temperature was set to 140 Celsius and the lower to 0 Celsius. The duration of the isothermal periods was set to 30 minutes. The total period of thermal cycle lasts 125 minutes. Following the heat treatment to which the study capacitors were subjected, changes in the capacitance, dissipation factor, and DSR values were observed. The structure and properties of the capacitor change. This work provides information on the evolution of the parameters of these capacitors under extreme operating conditions. The degradation of these capacitors can cause failures in the circuits and equipment to which they belong. Thank you very much for listening.
Okay, thank you for your presentation.
Can you stop sharing?
Questions? Online questions? No online questions. So it seems that this was the last work from outside the building, let's say. But as long as my colleagues prepared their presentations, poster presentations for the online part of the event, I will ask you to be patient and listen two or three more presentations. They are performed here, but they are also available online. Okay, so Ioana?
Mr. Păun, can you stop sharing?
Okay, thank you very much. Good afternoon.
You're welcome, thank you. Stai în locul meu, cum trec. Stai în locul meu, ca să audă.
Hello, I'll be short. My name is Ioana Anasiei. I'm from MNR, and today I'm going to talk with you about the realization process, method we use to valorificate our waste lithium batteries. In our work, we studied the conventional NCM cathode materials using the realization process compared with the hydrometallurgical or ferrometallurgical way. The realization is safer, and the economical and environmental impact is lower. We use in this process lithium carbonate as a source of lithium because it's safer and the economical impact is lower. We homogenize the black mass with the lithium carbonate in a planetary mill and sinterize at 150 Celsius degree for 5 or 4 hours. As can be seen in the table 1 and figure 1 and 2, the radiated cathode material using 4 hours of sinterizing, 5 hours of sinterizing is better. The extraction is more crystalline. It's the properties also are better in this case. I told you I'm going to be short, so this is all. Thank you very much for your attention, and thank you.
Okay. Thank you. Questions? What about online?
No.
No? Okay, Ioana.
No,
Yeah, please proceed with the second one.
Thank you.
And after you will be Steffi.
Okay.
Okay.
Thank you. The previous one was about the cathode materials. The cathode materials considered the most important component in lithium batteries, but anode materials also is important because the capacity and the safetiness and the working life for battery is dictated by this material. And in this work, we discuss a little about the conventional anode materials and their disadvantages and advantages, obviously. But we wanted to present a little about the high entropy transitional metals oxides, a new kind of oxides that are very interesting for the lithium batteries industry. There are many ways we can obtain this oxide by co-precipitation, combustion synthesis, salt gel, but also with a novel method, the oxidation of high entropy alloys. In this process, we elaborate HEA, high entropy alloys, in a furniture, induction furnace, and then we oxidize it in attritor for more than 40 hours. After this process, we can consider we obtain oxide, HETMO, but for a better oxidation process, we choose to use a pre-oxidation and Sitterings method. This also, we obtain the high entropy transitional oxide materials oxides by combustion synthesis, also a new method that also can be optimized in order to obtain better structural compositional. Okay. In conclusion, this is our work. We are very joyful to present it to you and very thank you to the organization of this conference. Thank you.
Okay.
Do you have any
questions?
No questions. For people online, I told you that this will be the end, but it seems that there are more people eager to present online. So please, people from the hall, come with your. I understand that there are 4 more.
Do you have it on stick?
I don't have it on stick because I thought that we need some posters. So if it's okay like this.
Îți aduc stick-ul mai bine. Nu, că e legat la...
I can shortly introduce myself and just put my poster on the phone. Just talk a little bit about my work. I will look if it's okay. Because my poster is in there, so we can stop the presentation in there.
If you
but
want.
the people online will have to see it also.
Oh, yeah.
Okay, let me skip from here and I remove the stick, but please come and told us and tell us which is îl aveți pe secțiuni.
Da, secțiunea a patra.
Cu modelarea.
Da.
Stai.
Cred că pot să-l recunosc mai ușor dacă... Nu, nu. Da, mai trebuie.
Ștefi, cred că sunt grămadă acolo. Uite-l pe ăsta, că aici sunt Isacul pe... Nicio problemă.
Da.
Yes, you can present.
Yeah, please.
Should I sit down?
Yeah.
If you want. Good afternoon, everyone. My name is Elisea Petre, and I'm a research assistant at the National Institute for Laser Plasma and Radiation Physics, and also a PhD student at the Polytechnica University of Bucharest. Today, I am pleased to present to you my poster titled Design and Experimental Validation of Zinc Oxide Heterostructures, alongside with my colleagues. So our purpose was to combine numerical simulations with experimental validation by engineering some parameters of the optical microcavity consisting of 2 Bragg mirrors and an active region of zinc oxide layer. So we choose zinc oxide because it is a fascinating semiconductor. First of all, it possesses a high excitonic binding energy that makes possible the excitonic emission and the strong like matter coupling even at room temperature. So this is why we choose zinc oxide. For the numerical simulations, we used a standard method, which is called transfer matrix method. So we can see how light propagates each layer of the multi-layer system, and then calculate the reflectance spectra. For the experimental part, first of all, our samples were obtained by pulse laser deposition. It's a technique that allows us precise control for layer thickness. The spectra obtained for experimental validation were performed by angle resolved reflectance. So you can see that the minima of these 2 spectra, the theoretical one and the experimental one, are corresponding. So we confirm the accuracy of the model. And what is important to know is that we have 2 resonances, the photonic one at approximately 400, which is the photonic one, and the excitonic one, which is specific to the material. As the angle of incidence increase, they are shifting to shorter wavelengths, but the photonic peak does not surpass the excitonic position. So this is a sign of anti-crossing effect. It's a sign of strong like matter coupling. So in conclusion, by engineering the optical parameters like layer thickness and the number of Bragg pairs for zinc oxide heterostructures, we can tune both resonances, the photonic and the excitonic one, and use them in zinc oxide based photonic devices or polariton lasers or even quantum light sources. Thank you. That was my presentation.
Questions? No? Okay. The next one. Era înscrisă la Young Researchers. Atunci nu cred că e.
Nu am mai. Hai, Cristina, nici. 2-3 minute.
Asta e? Ok, perfect.
Good afternoon. My name is.
Please,
I think that I prefer to say.
Yeah, you.
Yeah, it's okay. It's okay. It's okay. If you speak louder, they will hear.
It's difficult for me to see the. So I can Good afternoon. My name is Cristina Nitzer. I'm a researcher at the National Institute for Laser Plasma and Radiation Physics, and today I would like to present a study which was performed in collaboration with 2 other international institutes, one from France and one from China. During the last years, a lot of research have been focused on battery studies, this being one of the most important key for technology development. In the last period, the attention was focused more and more on lithium-ion batteries, especially due to high energy density. But the problem with lithium is the limited resources. So we are looking for other alternatives, and one of these is sodium, which presents similar chemical properties as lithium, but the resources are considered unlimited because they are everywhere in nature. In contrast with lithium-ion batteries, in case of sodium-ion batteries, graphite cannot be used as anode. So we need other type of carbon which are stable, cost-effective, and scalable. In this context, biomass derived hard carbon materials could be considered with high potential for this kind of application. The aim of our study was to obtain and compare 3 types of biomass-based carbon made of walnut shell, coconut shell, and cork silk. The protocol synthesis consists in a high thermal treatment at 1,300 degrees, followed by an acid washing. The materials were characterized from the structural point of view by XRD and Raman spectroscopy. The diffractograms present carbon with a low degree of characterization, and the report between ID and IG indicates that the carbon obtained by cork silk is the more organized carbon. This aspect was confirmed also by EM microscopy. In case of carbon based on walnut and coconut, all the structure is disordered. But as I said, in the case of carbon obtained by carbon silk, some organized areas could be observed. The textural properties were investigated by nitrogen absorption technique. In case of the carbon obtained from walnut and coconut, the type 4 isotherm could be observed. This indicates that these materials present also micropores and mesopores. And in the case of the carbon silk, we have only the presence of micropores, having an isotherm type 1. All the materials present a specific surface, low specific surface area, which is indicated for this kind of applications. The electrochemical, the materials were investigated also from the electrochemical point of view. Even if we have a high irreversible capacity in the first cycle, after the second cycle, we have a constant reversible capacity up to 100 cycles. So we can consider that we recommend these materials as good candidates for the application as anode in sodium ion batteries. I try to be very short. Thank you.
Okay, thank you. Questions, or we change the speaker? Yeah. So
section?
it was more successful than we thought. Which section? Good.
Okay, so I will be very short. My name is Ana. I'm from INFLPR. The whole idea of the project was so we have photodynamic therapy, which is a great therapy for cancer. But for photodynamic therapy, we need light from outside the body in order to activate a drug that kills cancer cells. Our idea was to make the light inside the body. So in this way, we can treat deep tissue tumors. We use cilium nanoparticles, CuTO2 nanoparticles, in order to have light from inside the body. So we irradiate the nanoparticles with the 7.5 petawatt system from ELI MP. And with this X-ray radiation, we managed to have some kind of nanolight in order to activate our photosynthesizer to kill the cancer cells. To see if our, I can use the mouse? Okay. To see if our project works, we use breast cells. And this is the triple negative breast cancer cell. And these are the normal breast cells. And after our experiments, we saw that irradiation, here are the irradiated one, irradiation kills the cancer cells after they are treated with our nanoparticles that are doped with the photosensitizer. And as a message, we managed to have some nanosystem that emit light inside the human body in order to kill breast tumors that cannot be usually treated with photodynamic therapy that is outside the body. So this is it.
Okay, so I think that no questions, but a lot of good luck.
Yes.
In your future work.
Yes,
Okay.
thank you.
Okay. Okay, there is any? Yeah, please. Deci ar fi dumneavoastră, colega mea și mai avem încă o cerere.
Avem vreun pointer?
Da, ce nume?
Ivan Raluca.
Ivan.
Da.
Da.
Okay, here?
Cât mai tare și ok.
Okay, so the time. Okay. Good afternoon. My name is Raluca Ivan. I'm from the National Institute for Lasers, Plasma and Radiation Physics. And today I would like to share with you the work behind our poster entitled Tailoring Functional Nanohybrids by Laser Engineering, Dual Applications in Energy and Environment. So our work had a starting point into measure global crises. One of them is the environmental pollution caused by the release of harmful organic contaminants into the water sources. And the other is the energy crisis, which requires usually eco-friendly approach for clean and effective energy storage. In this way, our goals was to develop some nanostructures that could respond to the both needed. So, in this way, we try to use commercial materials like graphene oxide, nanoparticles, carbon nanotubes, and also nitrogen and boron compound. And as a technique, we use a laser-based technique called matrix assistant pulse laser evaporation, or short MAPLE. Why we choose these techniques? Because our laser techniques allow us to reduce graphene oxide during the laser processing in order to obtain a graphene-like materials called reduced graphene oxide. And also we can dope with nitrogen or boron compound our layers during the same process, and also we can grow multi-component layers at room temperature without any additional treatment required by conventional techniques. Initially, we prepare dispersion of our commercial materials. Then these dispersions were sonicated and then cooled down anti-solidification in liquid nitrogen. And then our frozen target was put inside two chambers, and we irradiated it with the aid of a pulsed UV laser. So after the depositions, we investigated our layers by scanning electron microscopy. In the right part, in the first 4 images, you can see the results. As you can see our structures present porous structures, and also the transmission electron microscopy images confirm the presence of graphene oxide platelets, and also the presence of carbon nanotube, and the presence of some spherical nanoparticle incorporated into graphene oxide platelets. Also the FFT patterns confirmed the crystallinity of our sample. Furthermore, the XPS analysis also confirmed the reduction of graphene oxide during the laser processing, and also the incorporation of nitrogen and also boron in our layers. So after that, in order to demonstrate the functionality of our layers, we test them from water cleaning using methyl orange as the contaminant under simulated sunlight condition. Here in photocatalytic test, the best photocatalytic performance was obtained for our hybrid layers containing also nitrogen and boron compound. After that, the next step was to test our layers with electrochemical studies, and also in this case the best volumetric capacitance was obtained in case of our hybrid layers consisting of nitrogen and also boron compound. So just to conclude, I want to say that we believe that our laser techniques could be a powerful technique in order to develop hybrid nanostructures, in order to use them for many applications, for energy, and also for environmental application. Thank you so much.
Yes, please. You have one question.
How was the capacity of the reactor for photocatalytic evaluation?
We tested the volumetric capacitance by electrochemical study, not by photodegradation test.
Okay. And the temperature?
Room temperature.
Okay, thanks.
Welcome.
Okay, thank you. I will ask you to take the last one. It seems to be the last one from online, okay? And then come back to the hall. So, Mrs. Eliza Gabriela Broască, are you online? Are you with us anymore?
Hello, yes, I'm here.
Okay, it seems that we can hear each other. Please share your poster and proceed with your presentation.
Can you share it? Yes, one moment. One minute, sorry for the problem. Okay. Okay, so I will do the share screen. Is it okay?
Yes, we can see it now.
Well, so good afternoon. My name is Elisa Gabriela Broască, and today I will present you the study entitled Titanium Dioxide Thin Film Fabricated by PLD in Various Atmospheres for Efficient Methylene Blue Photodegradation. The aim of the research is to eliminate organic contaminants from wastewater. It is known that the multiple industries produce a significant amount of hazardous compounds such as dyes, which are toxic, non-biodegradable, and potentially carcinogenic. So in this study, we aimed to use photocatalysis to degrade methylene blue by using UV radiation and titanium dioxide thin films. Titanium dioxide are the most widely used semiconductor photocatalyst in wastewater treatment due to its low cost, stable nature, and optical absorption in UV region. So the advantages of using titanium dioxide in films in photodegradation or reaction are a fixed material in water solution, does not disperse, and reusability on more experiments and cost-effective ones. So initially we prepared the photocatalyst. So titanium dioxide films were deposited using furious laser deposition technique in various gas atmospheres, oxygen, nitrogen, argon, and atmosphere. The film are grown from titanium dioxide target on glass substrates. Here we can see that the wall samples display a surface with granular clustering and aggregation. In the case of sample deposited in argon, nitrogen, and helium atmosphere, a cauliflower-like morphology can be observed. And while the sample deposited in argon atmosphere, particles with spherical shapes are uniformly distributed. So the experiment were carried out using 40 micromolar methylene blue solution and titanium dioxide in films deposited in various atmospheres. So the experiments were carried out without and under UV radiation, and the reaction is considered complete when the absorption does not increase. The absorption spectrum of methylene blue is presented. The maximum absorption of the dye was recorded at 662 nanometers. Hypochromic effect can be observed in the case of the absorption process, and in the case of the solution exposed to UV radiation, we can see a hypochromic and a hypsochromic shift of the maximum absorption of methylene blue due to the degradation of auxochromic groups, methyl and methylamine present in the methylene blue structure. So the shoulder observed at 616 nanometers represents the dimeric form of methylene blue resulting from self-aggregation of the dye molecules. HPLC analysis was used to determine the reaction intermediates and the final product of methylene blue. As we can see, stepwise and methylation reaction of the organic dye take place, so with the methyl group being removed one by one, resulting in reaction intermediates, phenothiazine derivatives, and final products. The intermediates Azure A, B, C, and thionine have identified in accordance with data from literature. And the final degradation product with a lower molecular weight were formed as a result of aromatic ring opening. On comparing the degradation efficiency of methylene blue under UV radiation in the presence of titanium dioxide in films, it has been found that the maximum degradation in aqueous solution has occurred in the helium atmosphere. So a higher A constant means a faster reaction, as we can see in the photodegradation reaction in the presence of titanium dioxide in films deposited in helium atmosphere. Photocatalysis follows pseudo first-order kinetics, which can be observed to non-linear relationship in graphs. Finally, in conclusion, some micrographs reveal the critical role of gas atmosphere in shaping the surface morphology of titanium dioxide in films. Photocatalysis proved effective for methylene blue applied to different tin films. Titanium dioxide in films could be used to remove toxic organic compounds from wastewater, and HPLC was used to determine the degradation mechanism of methylene blue. Thank you for attention.
Okay, we thank you. Questions, please? No questions. Thank you once again.
Thank you very much.
Thank you. Miss? Can you join us, please?
What section?
Ce nume?
Maria Bălan.
Aproape de...
Hello, everyone. Thank you for the opportunity to present. I will be brief. What this study is about growing, primarily nanowires made of zinc oxide, but also other nanostructures, as you can see in the SEM images. And the method that we use to grow these nanostructures is called vapor liquid solid. And for material source, we used laser ablation plasma that was produced in a pulse laser deposition setup. This method uses a liquid gold droplet as a catalyst for nanowire formation, and the nanowire grows underneath the catalyst droplet. However, based on the growth condition, we can obtain different morphologies, and we can obtain thinner or nanowires or thicker structures that are alike to nanorods or even other morphologies. And also we varied the growth substrate. So we did some, we grew some zinc oxide nanowires on quartz and also on a sapphire substrate with a specific cut that has a very good lattice match with zinc oxide. And we obtained very well-aligned nanowires on sapphire, while on quartz they are in different directions. And also we grew some nanostructures on the unpolished side of the sapphire substrate, and thus we obtained some more multi-scale nanostructures. These nanostructures were grown for the application of using them as targets for laser particle acceleration, but they can be used for many other applications as well, since zinc oxide is very versatile. And we also did some light absorption simulations, and we saw that with an increase in nanowire length, we have also an increase in absorption in the visible range. And yes, that's basically all. Thank you. If you have any other questions, I'm happy to answer them.
Okay. No questions? No, thank you.
Thank you.
And we are having the last poster presentation with online audience. So, Stefania, please.
Thank you. So it seems like I'm the last one. My name is Stefania Caramarin. I'm and also I'm a PhD student at the Polytechnica University of Bucharest. And I'm going to present you today a very short, a small part of my PhD thesis about sol gel derived Baghdadite powders. Baghdadite is a compound that was found in some mineralogical ores in Baghdad, Iraq. So from there the name Baghdadite. It's a calcium zirconium silicate with outstanding bioactivity and the capacity to stimulate osteogenic cell proliferation. And the sol gel method enables low temperature synthesis of nanostructured powders with controlled composition. And our research question first was if the sol gel method can provide phase pure nanostructured Baghdadite powder suitable for bone tissue engineering. So, like I said, we proceed with the sol gel synthesis, and we wanted to find out if the precursor salts that we use have an influence of the structural and morphological characteristic of this compound. And as you can see in this table, I think it's quite small. We did some precursor combinations from calcium and the zirconium salts. We used the nitrates or chlorides. and tetraethyl orthosilicate as silicon precursor. We did this combination, calcium nitrate and zirconium chloride, or both nitrates, both chlorides. And all these four powders we analyzed by FTIR, BET, SEM, and XRD. And we found that the best combination for obtaining powders closest to the theoretical stoichiometry was the calcium nitrate and the zirconium chloride. But we calcined them only at 900 Celsius degrees. So from the XRD analysis, we found that we have also some secondary phases. So in our next steps, we want to go up with the calcination, maybe at a higher temperature or a longer time, in order to obtain only the phase, the pure phase of the baghdadite, to eliminate the secondary phases. So that's it from my part from now, and thank you for your attention.
Questions?
You have such an image there. You have some connection with Fuller.
With Fuller?
Your image there.
No, it's just for the presentation to look better. No fullerene in my compound. It's a silicate, a calcium silicate with zirconium incorporated in the lattice.
Okay, so no questions.
I think we have one.
Yeah, we have one more from.
So I wasn't
online.
the last one.
Okay, the person requesting
I can see the name.
for the online presentation. Can you hear us?
Yes, I can hear you. Can you hear me?
Okay, yes, we can hear you, and you are?
I am Matei Mortic.
Okay, please, can you share
yes,
the
I'm
presentation, please?
I will share right now. Please let me know if you can see the poster.
Yes, we can see.
All right, perfect. So thank you very much. Good afternoon, everyone. My name is Matei Mortic, and I'm a high school student. This project was prepared with together with Dr. Marian Zamfirescu from INFL-PRM. The motivation behind this study was to obtain optical elements capable of generating beams carrying orbital angular momentum, or OAMs, or OAM, by using spiral phase plates, shortly SPPs. Such plates introduce a phase shift that increases continuously with the azimuthal angle, and thus transforming a conventional Gaussian beam into a vortex beam. We were interested in evaluating whether two-photon polymerization, a high-resolution 3D lithography process, can reproduce the spiral phase profile required for high-quality OAM generation, and which would be the ideal internal structure of such SPPs in order to generate clear OAM, orbital angular momentum beams. Next, I think it is quite important to highlight the design process, and thus we designed several spiral plates with different topological charges and geometrical parameters, as you can see here, controlling the height variation to obtain desired phase distribution. The fabrication was performed using a nanoscribe photonic system in an IP deep photoresist on a glass substrate. We we used the various exposure parameters, such as the laser power or exposure time. These parameters were optimized to ensure both surface smoothness and structural stability. After writing, the samples were developed and were microscopically assessed. Afterwards, we performed some optical testing by illuminating the samples with a laser beam and observing the resulting intensity parameters in the far field, as shown in the images. This is the experimental setup we used in order to assess the state of the SPPs and their structural characteristics. As shown in the images here, the beam acquires the characteristic donut-shaped intensity profile, which we are trying to obtain, conforming thus that we successfully generated optical vortices, yeah, thus clearly showcasing the fact that fabricating spiral faceplates can be done using photon to photon polymerization, and that's all from my part. Thank you very much for your time.
We thank you for your presentation. Questions, please? Online questions? No. Are there any requests from online? So, for the online audience, we stop here. We thank you for attendance. We are waiting for you tomorrow at the same hour, using the procedure that you discovered today. Once again, thank you for your presence and your contributions, and have a nice day. For people in the room,